Alrighty, so in this video, I'm going to work through problem 2.2 in Griffiths E&M book. And you know, the first thing we do is just evaluate the little example he gave us before the problem. Yeah, so in this example here, he gives us like a setup where you have these two charges and you're looking at the electric field. What is the electric field at some point P, some distance Z above the center of these two charges. And for problem 2.2, see, notice both of these charges are exactly the same. They're both either positive or they're both either negative. Point being, they're both exactly the same magnitude, same sign of charge. While in problem 2.2, the variation is that the charge at the x, at the position x equals plus d over 2. So this charge over here is negative. So let's find out what's the electric field at this point P here for that kind of slight alteration. Okay, so let's sort of draw the setup real quick. Point P, some distance Z. This length here is d over 2. This over here is d over 2. The total distance between these charges is, of course, d. And now comes the part where we start evaluating sort of how we tackle this problem. Let's bring up a equation here. So let's bring up F equals Q E. So this is the Coulomb force equation defined in terms of the electric field. And this leaves us with that the electric field must be then defined as 4 pi epsilon naught Q R squared. Okay, so what does this imply? First off, this equation here is a scalar equation. So, you know, we're not thinking about directionality, just in general. This equation tells us that, suppose you have two particles right here. Both equally charged, both equal magnitudes. They will experience a repulsive force in equal and opposite directions of equal magnitudes. And so if we strip away this charge here, the electric field then must be in the same direction as the force. Because of course that is what this equation is saying. Okay. So now we can evaluate electric fields at different points without needing, at least theoretically speaking, a test charge. There is no charge to test here. There is no charge there. This equation allows us to do that. With that being said, I still find it conventional to, at the point that you're evaluating, to find the electric field, to assign it a sign, either positive or negative, and you stick with that during the entire calculation. In this case, I arbitrarily say, well, if there was a charge there, it would be, I'd like it to be positive. We don't have to analyze this here. We're looking at point P. And from this interaction, if there was a charge there, it'd go that way. And arbitrarily, I'd say I assign that to be the magnitude of the electric field. So the same direction. E1, R1. Okay. Now I turn my focus to this interaction here. You can do this type of like interaction to interaction addition, so to speak, because of the superposition principle, meaning that E is comprised of E plus 1, E1, E2, and so on. We can construct the net electric field by the sum of the individual electric fields produced by each interaction, one at a time. So in this case, we have philosophically here a if positive charge. If there was a charge there, it'd be positive, and it would go towards the negative. Okay? And I'd call this E2. Let me go ahead and put this vector somewhere over here. And this length here, that would be R2. Notice that because of the symmetry of the problem, we could say that R1 is equal to R2, which is just equal to some number R. They're both equal to this number, whatever it is. That's another thing that simplifies our computation. Now, we continue doing a little bit of this kind of geometry to sort of simplify the actual computation that we're going to do. So, of course, both of these vectors are exactly the same lengths, it's just they're different directions. And so, suppose I say that the origin of this coordinate system is right there at that point. Just for convenience, this is your x and this is your y axes. 1, 2, 3, 4, 5, etc. Doesn't matter. This point here is 0. And now we want to evaluate the components of each of these vectors. So the vertical component of E1 is going to go something like this. And the vertical component for E2 is going to go something like this. And notice that I'm not going to go ahead and give names to these or anything. They are in opposite directions, so that's like saying +1 - 1. So it's equal to 0. They both cancel each other. So we're only left with looking at these kind of horizontal components. The horizontal component for E1 goes something like this. And the horizontal component for E2 goes something like this. And notice they are, again, the same magnitudes. That's all because of the symmetry of this problem. Notice that, again, they're the same magnitudes, so E1x is equal to E2x. So they are just equal to this one number. We're going to call it EX. They're the same magnitude. So that leaves us with E net being E1x is E2x. 0, because again, the vertical components canceled out. This is the vertical part of the vector. This is the horizontal part of the vector. Both of these are just equal to EX. So I'm just going to say 2EX. We're adding them up. Carry down to 0. And now we have to further define this EX. So supposing you have some triangle like this, E. This is theta. This is EY, this is EX. Then, according to trigonometry, EX can be defined as the magnitude of this electric field times cosine theta. Okay. We know this. The magnitude, what's happening here? Cosine theta. Magnitude of the electric field for point charges, at least, goes as 1/4 pi epsilon naught. Absolute value of Q. Reason being, we don't really care too much about these signs in this case, just because we've done the geometric work to know where will the electric field go at. It's going to go this way, so we don't have to worry about signs to tell us. We know where the electric field is going to go. So we just take the absolute value of our point charges. R squared cosine theta. Now, we want to express cosine theta in terms of known values. In our case, z and d over 2, d and z. And we can do that again because this problem is essentially two right triangles back to back. There's a lot of symmetry in this problem. See, this angle is equal to that. This angle here is equal to this one. Because again, you can make this little box, and if you have this diagonal going through, these angles are going to be the same. You can convince yourself and look at some geometry. Anyhow. So now, due to symmetry, again, we can just look at one side of the system. Let's say this side. This is equal to r, this is equal to z, and this is equal to d over 2. And according to trigonometry again, cosine theta is defined as adjacent over hypotenuse. Opposite would be this one, because it's opposite to this angle. In this case, d over 2 is actually adjacent to the angle. I believe that's the logic. Yeah, it'd be d over 2 over r. And notice that, again, this is a right triangle, so we can use Pythagorean theorem to further define r in terms of d over 2 and the z. So let's do that. So r squared is equal to d over 2 to the power 2 plus z over 2. We take the square root. And in this case, we only care about the magnitude of this r. So we can do away with this negative here. Choose it to be positive. And r, the square root can also be written as this argument here exponentiated to 1/2. This will prove to be useful down the problem, just for simplification purposes. Now, we bring this down. Ex is equal to 1 over 4 pi epsilon naught, magnitude of q. Again, notice those two r squares. So we can just say, bring this argument over here. This cosine, definition right there, r right here. Bring this entire thing down there. Okay. d over 2 over d over 2 to the power 2 z squared to the power 1/2. Now, again, the reason we chose to write it as in terms of powers and not square roots is because now, we can easily see that both of these arguments are exactly the same. This here is also equal to that. Argument exponentiated to the power 1 is just the same thing. And now we can combine these two and just write one argument to the power of the sum 1 plus 1 over 2 is equal to 3 over 2, or 1.5. I like to keep it in fractions, just because I think it looks a bit more neater. It's just mathematical kind of preference. 1 over 4 pi epsilon naught. 3 over 2 squared plus z over 2. 3 over 2 absolute value q d over 2. Sort of bring it out. Now, we have to go back up here. Now we're ready to assemble our solution, so to speak. So E net, or actually, no, E net. I'm not going to write it like this anymore. We're not going to write it in this form. Okay. What I'm going to do is, I'm going to say E net two times d over 2, just rearranging. And I'm just going to include the component that's actually active, which is the x component. Because ultimately our electric field is in the x direction. Sorry, this cancels. Now we're left with E net is equal to and that's it. That's sort of the analytical solution. Alrighty. My refrigerator just turned on. But yeah, what does this equation mean? What does it mean? Well, of course, it means that the electric field in the x or the positive x direction. But the big picture here is that this is a dipole. This is a dipole. It's a dipole arrangement, meaning that you have one side that's positive, you have another side that's negative. And the behavior of the electric field is going to be something like this. Actually, let me choose another color for the electric field. Say something like green. How about that? Okay. Yeah, so if you were to do this calculation for a series of points all around, you'd end up finding out that generally the electric field kind of looks something like this. Of course, there's going to be infinitely many of these little arrows here. Infinitely many of them. Generally, the electric field, okay, it's going to look something like this. It's going to connect down here. And I'd say that yes, that our calculation does kind of agree with this kind of idea of the dipole. Where you have these, they call here these sources of the electric fields spouting out electric field, and these sinks of electric field consuming it. And in some sense, that's kind of the definition of charge, at least in this classical electrodynamics kind of regime. The charge itself is this, can be viewed as electric fields either coming out or electric fields diving in. The dipole. Yeah, I'd say that was the video. I hope it helps. Yep, have a good one.